The global ocean once contained all the life on Earth. It may still sustain 80% of it, most of it at depths where humans can't survive. Now, for the first time in human history, technology is taking us into the darkness and crushing pressure of the deep seas, into a world of mystery and surprise. What's down here? What is its nature? What are its secrets? Scientists, today's explorers, are in a race to answer these questions before our oceans are laid waste by our reckless actions. The research vessel Thomas G. Thompson is en route to the volcanic seamounts of the Pacific Ring of Fire, a place where few humans have ventured. Since 2002, there have been 6 such voyages. Canadian biologist Verena Tunnicliffe has been on 3 of them. Their objective: to map and survey some of the most dramatic undersea topography on Earth. Setting out from the island of Guam, itself a product of ancient volcanoes, Verena joins 20 scientists from 4 countries and multiple disciplines, all eager to find what lies in this great unknown.
We targeted the subsea volcanoes along the Mariana volcanic arc. And I think the most amazing thing that we came back with was that everything was new. We've seen a lot, my buddies and I, going out to sea, and it was like going to sea for the first time again.
Principal tool for exploration is a remote submersible called Jason 2. Able to cruise with ease in pressures that would crush most submarines, it carries tools, sensors, and multiple cameras wired to a control pod on the Thompson's deck, where scientists prepare to probe the mysteries of the Mariana Arc. The Mariana Arc follows the Mariana Trench, the deepest place on Earth, where the Pacific tectonic plate collides with the Philippine plate and plunges into the Earth's mantle, creating a trench 11,000 meters deep. And rising up behind it, a towering range of seamounts, submarine volcanoes. Soon enough, Jason reaches 400 meters and the peak of the first seamount, and a cruise of discovery begins. Down here, a submersible with its blazing lights can be a startling intruder.
Ooh, wow. We're disturbing all the crabs, all the squat lobsters that are around the bottom, and look at that. It's just a snowstorm of these crabs. And now they're all floating back down to the bottom, parachuting out of the sky.
And just over the crest, the unexpected.
Oh my God!
400 meters under the sea, a lake of molten sulphur.
Yes, it blew up and then all that gas came out. You see the whole thing kind of...
Then another surprise, lying right on the sulphur surface.
There's a flatfish down there. He doesn't care.
If it doesn't cook him, it should poison him. Yet the flatfish seems untroubled by a 200-degree vent of boiling sulphur.
Spongy liquid. Oh, look, you've got liquid coming up around it. You nailed it.
A crab wades into the molten sulphur.
He's cooked, man. Let's have a look. Poor guy. Is he going to make it? He deserves a medal. Wow. That dude is tough.
But the ultimate discovery is revealed below the pool, under clouds of rising sulphur.
You realize the bottom is absolutely covered by these little flatfish, and they're just flapping all over. It's like little butterflies all over the bottom.
What keeps them here is anyone's guess. Then a clue to the mystery comes drifting down.
I want to make a note that a dead fish just landed on the bottom. It was a mid-water fish. Well, that's the third one I've seen now in a while. It's not the flatfish, it's the ones from the mid... Oh, look at that.
Eventually, they compare notes and come up with a likely explanation. The nearby sulphur vents act as a natural trap, poisoning passing fish, which then sink to become dinner for the flatfish, who are somehow immune to this chemical soup. It's a biological wonder, the discovery of a whole new food chain capable of survival at such extremes.
It was amazing, the density of them. I don't think anybody's ever seen fish in that kind of density around hot vents before, and a brand new species.
That brand new species is important. Along with 2,000 other biologists around the world, Verena contributes to the Census of Marine Life, an international project to document all the life in the world's oceans.
Eocarnelasmus represents the most primitive living bellanomorph. But that's not what this guy is.
Steadily, they make their way along the chain of volcanic seamounts, sampling, collecting, measuring, and sending Jason on dive after dive to probe this alien world beneath their ship.
Every volcano we went to was something different, a different community, a different set of chemistry, a different set of conditions, a different behavior in the volcanoes, and new animals and new communities everywhere.
It's a bonanza for Verena, but 20 scientists share control of Jason, and Bill Chadwick, senior marine geologist, is less concerned with shrimp and flatfish. His quarry is an erupting volcano, but so far he's seen only steam vents and sulfur plumes.
So what's next? Go up to fault shrimp.
It seems like every dive is a little more exciting than the last, so I'm kind of looking forward to the next few days.
Then, during a night dive on a seamount called Northwest Rota, it's Bill Chadwick's shift.
Yeah, well, once you know the scale of that, yeah. We're over the summit, going down, and we started seeing the edge of this giant plume. Yeah, on the right, in the lower right there. That's it right there, huh?
Camera shaking vibrations tell them this is no ordinary vent.
Cool. Wow, look at that. What a great view.
This is the first time anybody's seen this.
Oh my God, look at that. Oh! 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 Wow. Look look at that red. Holy cow. Last night, it's just jaw-dropping. And the seafloor shaking, and there's lava coming up in the vent, and there's exploding gases, and rocks are being shoved out of the way, and everybody is just going, whoa! So not only are we learning about how these eruptions happen and how they affect the environment, but it's just incredibly exciting research to witness. So that makes it really fun.
It's the explorer's reward, the first continuously erupting volcano ever discovered under the sea, a scientific coup and a research tool for years to come. Surprisingly, for such a violent place, it has something for the biologist too.
On Northwest Rhoda, there are 2 species of shrimp. One of them is a brand new species, and this particular species has done incredibly well. There's very little competition. Nobody else wants to live there, and yet there's a lovely food source. And so perhaps they've become cued to those volcanic emissions that other species hate, that kill them, and yet they go, aha, a whiff of sulphur, and I'm going to go down and follow that sulphur cue.
Oh, got a few in there. It's a nice big fat one on that rock there.
Discovery is only the beginning of exploration. Scientists have known about seamounts for a long time, but it's only in the last few decades that they've come to suspect their crucial role in the ocean environment. Where seamounts rise near the surface, they often create local environments as nutrient-rich bottom waters rise up the slopes to support everything from coral reefs to teeming schools of fish. A volcano's transformation into habitat is poorly understood, and exploring the Mariana Arc may help explain the process. Perpetual darkness, unvarying cold, and crushing pressure make the deep ocean more hostile to humans than outer space. And we've only been coming down here since about the same time we started going up there. In the 4th century BC, Alexander the Great is said to have used an inverted glass jar, the first recorded diving bell, to dive beneath the Mediterranean near the ancient city of Tyre. The open-bottom diving bell limited us to dives under 20 meters until well into the last century. In the late 1920s, Otis Barton built the bathysphere for William Beebe. In 1934, they rode their 2.5-ton bowling ball to a depth of 923 meters, where Beebe reported seeing creatures that glowed with their own light. The deep sea, he said, sparkled like the night sky and teemed with outlandish life forms. Many thought his greatest talent was imagination. The next great milestone came in 1960 when the bathyscaphe Trieste carried 2 pioneers down 11 kilometers to the bottom of the Challenger Deep, the lowest point on Earth. They sat there for 20 minutes, then rowed it back up. It was a remarkable achievement. No one has ever gone back.
That remoteness, that inaccessibility has served to protect the ocean from a great many forms of human perturbation. And it means also that we seldom appreciate how significant it is in the ecology of the whole planet. And it's home to the largest animal communities on Earth, largest in terms of number of individuals, largest in terms of number of species, largest in terms of biomass. Most of the animals on this planet live in the deep sea.
Now working out of the Monterey Bay Aquarium Research Institute in California, Bruce Robeson has been investigating these animals since the 1970s.
I had been sampling the oceanic water column with nets the way a century's worth of my predecessors had done. It occurred to me that any self-respecting desert ecologist or forest ecologist would never attempt to describe the desert or the forest without ever having been there, and yet that's what I was doing.
In 1974, Robeson hitched a ride into the deep on Elvin, the first of the modern research submersibles.
The dive itself was a benthic dive. We were working on the seafloor, but in order to get there, you have to pass through the water column. And I kept turning on the lights, and the pilot would say, "Turn those things off. We need them for working on the bottom." But I wanted to see what was going by my window. I was thunderstruck. There were so many more animals than I had ever imagined, particularly the gelatinous forms. They were all over the place. They were really abundant, and they were zipping around and moving and swimming and showing all kinds of active behavior. Again, something that I was unprepared for.
Today, Dr. Robeson still spends about 50 days a year at sea, studying the animals that live below 200 meters under the surface.
As I used to say to my students, there's only so much you can learn from a dead fish. There's a great deal more to be learned by entering the habitat, seeing the animals in their natural environment.
Setting out from California's Monterey Bay Aquarium, the Western Flyer sails through some of the best researched deep water in the world. Monterey Bay is the focal point of a national marine sanctuary. And because the deep begins so close to shore, it's a favorite destination for explorers. Yet so vast is the ocean in relation to our understanding that every trip holds the promise of surprise, of discovery. Once on station, the crew prepares to launch Mabari's latest submersible, the Doc Ricketts. And another control room fires up in anticipation. As it descends, the Doc Ricketts passes first through the upper waters, home to most of the species we know, from sardines to sharks and everything between. Here, light and oxygen support life in all its abundance. Somewhere around 200 meters, the mesopelagic or midwater zone begins, and things start to get strange. Without the submersible's headlamps, light is too faint for surface eyes to see, too faint to support plant life. That doesn't mean there is no light, because from here down, creatures create their own.
Bioluminescence is apparent in animals throughout the water column. But as you go deeper, bioluminescence becomes more and more important as the only means of communication that we're aware of.
Most animals produce their own bioluminescence. Others achieve it by giving a home to photoactive bacteria, who repay the favor through advertising. Like cars on a freeway at night, these creatures are communicating through light, saying, "Come closer," or "Stay away." Certain celebrated species of shrimp can even vomit a sort of bioluminescent pepper spray that temporarily blinds an attacker.
My colleague Edie Witter says that, looked at objectively, bioluminescence is the most important communication form on Earth. And I'm sure she's right because of the vast numbers of plants and animals that create light in order to communicate with one another, to avoid predation, to attract prey, and for all kinds of other interactions.
In other words, more creatures use light to communicate than all forms of sound put together, from cricket chirps to human language. And when it comes to bizarre and creative solutions to the challenges of life in the deep sea, bioluminescence is only the beginning. Somewhere below 600 meters, Bruce Robeson's remote submersible closes in on a vampire squid. The capture and classification of specimens is a crucial element in the second stage of exploration, making sense of what's down there. But some truly alien creatures defy both capture and classification. Case in point, the largest member of a family called siphonophores, possibly the longest animal organism on Earth.
The largest siphonophore we've ever measured was 41 meters in length. Siphonophores are gelatinous predators that send out a curtain of tentacles that will capture anything that happens to blunder into it. They are unusual in that they're colonial animals.
That doesn't mean they gather in colonies, it means they are colonies. What seems like an almost endless undersea snake is in fact thousands of animals linked together to act cooperatively and share resources. This arrangement has been so successful that nature has found hundreds of ways to express it.
Like ant colonies, there are specialized individuals who have particular functional roles within the community. There are propulsive units. There are individuals that are reproductive elements. There are individuals whose role is to catch and digest food.
Because no land animal organizes itself this way, scientists can't decide how to classify it.
Do you treat it as a colony? Do you treat it as an individual? Or do you think of it as some sort of superorganism, which is often the fallback position? Well, it's special, it's not like anything else. We'll call it a superorganism and leave it at that.
Those deadly tentacles feed more than just their owners, and watching siphonophores led to the solution of the decades-old mystery of a little fish with big green eyes.
Macropinna is a little fish that we have known about for a great many years from net-caught specimens. When we first came across one, we were astonished to see that there was a transparent shield over the top of its head. Every specimen that I'd seen was drawn without transparent shield. We were well aware that they had tubular eyes that looked upward, and it always puzzled me that they seemed not to be able to include their mouth in the field of view of their upward-looking eyes. And how can you feed effectively if you can't see what you're eating? Well, as soon as we began to observe these animals in their natural habitat, everything came clear. And we've been able to determine that the eyes are capable of rotating from their upward-looking position to a forward-looking position. And these animals probably swim along beneath large siphonophores. When it sees something in the tentacles, it rotates the body and the mouth upwards, grabs the food, rotates the body back down, and proceeds down the linear smorgasbord of food that the siphonophore provides. The transparent shield protects them from the stinging cells in the tentacles of the siphonophore that they're swiping food from. The paradox of how that fish could see to eat was suddenly resolved by the fact that we could enter its habitat and watch it firsthand. We have been able to bring 2 specimens of Macropinna alive to the surface to confirm the observations that we'd made with the ROV. It's important to be able to make measurements in the lab that confirm what you see in the ocean, and vice versa. If you do laboratory experiments, it's very important to be able to confirm your results in the natural habitat.
But not today. And that's the lesson of these tales of deep-sea adventure. Until we explore and document the ocean's secrets, the splendid life within it remains a mystery and risks becoming a casualty.
We don't know what we don't know, that's for sure. We suspect that there's a hell of a lot we don't know, and we can categorize it, but there are only a few places where we can say we have even gotten a good start.
Vast ocean, vast ignorance, small resources. To find the right questions and begin expanding on the answers, we need more information as fast and as efficiently as we can collect it. One solution is to enlist the animals themselves in our exploration of their world.
If you look out there in the ocean behind me, you can't see anything below the surface, just sitting here. And so the real challenge is how to make that transparent. How do we look at these animals in that habitat? What that's meant is we've had to develop tools to allow us to follow these animals, to recreate the movement patterns, to basically tell stories about where these animals go and why they go where they
go. Project TOP, tagging of Pacific predators, follows 23 species, of which elephant seals are just one.
So what we've done is develop basic little tiny computers that are data loggers that routinely take information on the water temperature, the pressure, the swim speed, sometimes heart rate. And we put these tags out on the animals and let the animal go and do what it does, and then we recover the tags, or we have the tags relay the information via satellite. And then we can reconstruct what the animal's doing, where it's going, and what is the environment around the animal.
In practice, these involuntary researchers have lived up to expectations, and their data have been telling.
These are the elephant seals from Año Nuevo, and then we'll see elephant seals down here from San Benitos Island. So these are 2 different colonies. And you can see that even though the animals from San Benitos leave much further south, they're using the same region of the ocean. And yet, see, they come down to here, and the Año Nuevo animals go back to there.
And the electronic spies report not just where they go, but what they do on the way.
So this shows an 8-month trip in an elephant seal, and their dives are consistently in the range between 400 and 800 meters.
In a nutshell, the graph tells us that this animal spends more than 80% of its life in the near freezing darkness of the deep sea. The beach loungers we thought we knew turn out to have another life as deep sea hunters. And the data also revealed to the scientists' surprise that after a 40-minute dive, the seal needs only 2 minutes to replenish the oxygen in its massive blood supply. Previously considered biologically impossible, the discovery illustrates how life survives at extreme depths. Meanwhile, across the continent, tuna taggers are discovering that Western and Eastern Atlantic tuna, always thought to be totally separate populations, actually come together during part of the season. And through tagging of several species of shark, researchers can track them to discover the areas of high productivity where they find their prey.
Go ahead and get him. Right there. Good one.
And we're also finding areas in the ocean that are hotspots in terms of regions where many species, where you'll find an albatross, an elephant seal, a fur seal, a whale, and a bluefin tuna, all using the same region of the ocean. And I look back at some of the images we had when we were proposing this program, and there were arrows in the ocean saying, we think animals go this way, we think animals go that way. And now, 5, 10 years later, we actually have very detailed road maps of where these animals are going.
These road maps are revealing a network of subsurface superhighways. It's the beginning of understanding how the oceans work, and understanding becomes more urgent every day because not knowing how the oceans work has never kept us out of them. For most of our history, fishing has been restricted to the species of the shallow and coastal waters. Many deep-sea fishes never venture up this far, and that kept them out of our seafood diet. But in the late 20th century, technology made commercial deep-sea fishing practical. This came just as catch rates in most coastal and traditional fisheries were facing a long, slow fall.
So what we see is that, particularly say in the 60s, 70s, and 80s, we were looking for new resources, and particularly the Japanese, the Russians, some other nations, moved deeper and deeper down the continental slope into the deep sea.
The situation has only worsened. Boris Worm, himself an undersea enthusiast, shocked the world by announcing that under current fishing practice, humanity's seafood supply, all of it, will be gone by mid-century.
We collected records going back hundreds of years to track the depletion of fisheries. And what we found was that there was a slow depletion of marine species over the last 1,000, 2,000 years even, but accelerating over the last 100 to 200 years. So that we're at a point now where every year there's a larger number of species collapse, meaning where that can't be commercially fished anymore. If that trend would continue, if you wouldn't change anything, just keep down that track, we would run out of seafood resources by the year 2048 or so.
Fishers hoped that the deep seas could fill the growing shortfall. They dropped their nets to 500 meters, then 1,000, with little idea of what they might find or where they'd find it. On the seamounts off New Zealand, about a kilometer down, they found a winner.
Science had known about orange roughies since the late 1800s, but basically they lived undisturbed for many millennia until the mid-1970s when they discovered orange roughy in New Zealand waters on the East Chatham Rise.
Orange roughy was commercially ideal, a mild white meat that held its firm texture through freezing and thawing. It looked like the deep seas might indeed have solved the problem of declining shallow water stocks, especially as other concentrations were discovered in the Pacific, Indian, and North Atlantic Oceans. Ships from many nations created a deep-sea gold rush, most with no quotas to restrain them. They mined the sea, and when catches got ahead of demand, many tons of valuable roughy went into landfills. The wholesale slaughter continued until catch rates began to fall far faster than anyone expected. This was particularly disturbing in New Zealand, where roughy had been a bonanza for the country's small economy, and regulators were determined to make it sustainable. Because almost every zone they fished fell within their national waters, they could set quotas. To enforce them, they sent out regular air patrols to detect and deter cheaters, just as Canada does, just as many maritime nations do. Yet even though they could be fairly sure fishers were keeping to quotas, catches kept on falling toward collapse. Fisheries scientists were asked to explain it.
There was a very steep learning curve for science in the 1980s, and it wasn't until the late 80s and the early 1990s that we began to discover important aspects of their biology.
The truth was, there were huge gaps in their scientific knowledge, brushed aside in the rush to exploit the resource. Scientists knew almost nothing of the roughy, except that it congregated near the bottom between 800 and 1,200 meters deep. They had based quotas on experience with shallow water species, and evidently, something was wrong. The first imperative was to get an accurate picture of the roughy's lifespan and rate of reproduction.
So the way we actually age them is to use bones in their body, and the bones in their body they're like trees, and trees have growth rings, and fish bones will actually do the same thing. And so we can use it to measure how old they are. The bones that we choose to take are the ones from their inner ear, which sit just behind the brain. And we take them out, and then we section them, and then we actually have to put them under a microscope to see the rings. Okay, so what do we got here?
This is one of the Cordella ones.
We started looking at the ear bones in the late 1980s, and that came in and showed them to live to 100 years or more. And that actually generated a lot of controversy when it first happened.
47's a faint one, 48, 49, 50, and possibly a 51st one right on the end.
Fishes often live 20, 30 years, but the idea of a fish living to 100 years was unheard of at the time.
In fact, it was key to solving their puzzle. Determining age is important because short-lived animals must reproduce much more quickly than long-lived animals. So taking 20% a year from a short-lived population may have no net effect on stocks because natural reproduction replaces it. But a long-lived animal may only reproduce 10% a year, so taking 20% of its population will result in just what was happening: rapid depletion. Research on young roughies confirmed their findings.
Okay, so what we've got here, first one will be about a year old, and these ones here will be slightly less than a year or so. By the time you get to 2 to 3 years old, they haven't really grown much more. So you can see how slowly they grow.
They concluded that roughy probably don't even begin to reproduce until at least 30 years old, greater than their previously assumed lifespan. By the time the government and industry reluctantly accepted their evidence, it was already too late for most of the planet. The roughy stocks collapsed.
The Australian fishery is effectively closed. There's one small fishery remaining. The Chilean fishery is closed. The EU are planning to close, I understand, planning to close their orange roughy fishing from next year. The Namibian fishery has been reduced to a low level. So the New Zealand fishery is continuing, and in a way it was the first, and it looks as though it may well be the last remaining substantial orange roughy fishery.
With industry support, New Zealand has closed fishing grounds and drastically reduced quotas in the hope of stopping the collapse and even reversing the damage. Many believe it's too little, too late. But on the other side of the world, Boris Worm has followed the fate of other endangered fisheries.
I don't think it's too late to change things, and what gives me hope is that increasingly we see where people are doing a good job and where they're trying to manage things sustainably. We see recovery of fish stocks, we see rebounding both close to shore and on the high seas. Swordfish stocks in this region, for example, have been increasing recently due to good management, and that's really a sign of hope.
Encouraging news, but this research too is based on stocks of shallow water fish, and as we now know, what works near the surface may not apply 1,000 meters down. In any case, even if stocks recover, New Zealand's problems with the orange roughy fishery don't end with overfishing. There is a secondary issue that excites the concern of activists and has become a focus for researchers. That issue is the destruction of the deep sea habitat. Orange roughy hug the sea bottom for protection, and in these waters, that means the slopes of seamounts. To catch them, trawls must be dragged directly along these slopes. So the scientists on the fisheries vessel Tangaroa study both fished and unfished seamounts to assess the impact of trawling.
Sandy sediment down the base. Coral ribble, some Gorgonian corals to the left.
The orange roughy just hanging there, motionless. The fishing gear used for orange roughy fishing at those depths weighs about 3 tons. So the impact on fragile fauna, on vulnerable fauna like corals and sponges is considerable.
The effects of bottom trawling were known, but no one thought to find out what the roughy's habitat contained before plunging in with seabed scouring gear. Now, we can only assess the damage.
The difference between fished and unfished seamounts is very strong. Where seamounts have been heavily trawled by heavy bottom gear used in orange roughy fishing, the sponges, corals, they do get damaged and impacted heavily by the commercial trawl gear.
That impact is unmistakable in these undersea images. Seamount slopes are not agricultural farmland where great change comes with every season. Down here, temperature and light levels barely fluctuate by terrestrial standards. Undisturbed for millennia, these corals and sponges have never adapted to change.
Our belief is that these deep-water coral reefs have developed over thousands of years. The growth rate of those corals is very slow. We think it's only millimeters per year. So any recovery, if in fact it can occur at all, is going to be very, very slow.
The orange roughy story isn't over, but its lesson is clear. Exploiting the deep sea without properly understanding its complexities puts the largest ecosystem on the planet at risk. To create a new relationship with the ocean, we have to reimagine it as the three-dimensional world that it is, and that is a radical new way of thinking. If the creatures of the deep could study us as we study them, they would probably think our waterless habitat is impoverished, barely capable of sustaining life. Exposed to appalling extremes of light and temperature, we are mere bottom crawlers, gravity's prisoners, condemned to live in 2 dimensions on the floor of our atmospheric sea. In contrast, the deep sea is a far more hospitable place for life. Predictable, stable, effectively without limits, for most creatures will never encounter a solid surface, where up and down are just directions, as available as forward and back are to us.
All right, safety harnesses secure.
A few broad-minded terrestrials grasp this essential difference between our planet's 2 worlds, and prominent among them is Graham Hawkes, an engineer who has spent his life learning how to become a traveler in the depths.
We're just not accustomed to thinking 3-dimensionally, so I think we take our terrestrial view of things and imprint it on the ocean. So our view of the ocean is it has this surface and it has this surface. And if we can move on that one and that one and travel between them, we're done. But this 3-dimensional space, that is this planet. 94% of life on Earth lives in there. Some of us think we have to learn to move and master that 3-dimensional space as the animals have. I mean, if you look at the sea lions here, they don't open valves and sink up and down and then try and catch a fish on the way. They zoom We need to fly in that space the same way that we have the freedom to fly in airspace and the freedom to fly in near space. This is no different. For some reason, it's taken 100 years since we first flew in airspace to fly in blue space. And I can't explain why it took that long.
Designed to operate down to 300 meters, the Super Falcon is an expression of Hawke's philosophy of ocean exploration. It was developed in reaction to conventional submersibles, including his own deep rover, which bristles with high-powered lights and heavy electric motors.
In the past, we've been so obnoxious, we've been painful to them. We go down with noisy vehicles, blasting out light that are going to damage eyeballs, and we expect to see things. It's kind of silly. I mean, let me try and give you an example. We're terrestrial, so we know enough that if we were doing a scientific expedition in the jungle to film a tiger, we don't go in with a marching band and smelly, stinky socks, making as much noise. But that's what we do in the ocean. So if we went into the jungle making a lot of noise and smelly socks, we'd come out and we'd have a press conference and we'd say, no lions and tigers and bears in there. We did see butterflies and slugs, and we found a footprint of a tiger. So we know they exist, but we think they're extremely rare. I think that's how silly we've been going into the ocean. So, first of all, we worked on making that sub very quiet. And with these machines, we've been getting very close to animals. And then we've learned to put very, actually low power, we call it mood lighting, around the submersible. So we try and probe ahead with lasers, and then we put the smallest amount of light out we can just around, so that anything we get close to, we can actually see. I think you're going to find in the future the machines we build in the ocean are elegant, beautiful, quiet, far more compatible with that environment, and quite comfortable for a whale to be swimming alongside one of our machines just flying alongside. I mean, that's a dream, when we can bring these machines close to these big animals and they're comfortable with us.
As noteworthy as the technology of deep flight is the shift in attitude it signals in our approach to the deep seas. It allows us to make the leap from distant observer to direct participant. If we're to make the deep sea part of our world, we'll have to go much further down this road, even as we greatly expand established methods of research. The potential of this vast world is so great that no amount of effort would be wasted, no amount of money spent in discovery too much. Yet ocean research receives a tiny fraction of the resources lavished on that other great frontier, space.
The question of why we spend more money in space and not the ocean, it doesn't make any sense to me whatsoever. Our whole future of mankind depends on understanding and working with the oceans. The oceans hold all of the minerals, food, energy, and space for expansion of the human race for the future. Not near space. Near space, it's a sterile vacuum. A great view. What else?
That view confirms what Graham Hawkes contends, that ours is an ocean planet. And if scientists are right about its importance to our future, there is no time to waste. But for the explorers themselves, those who spend their working lives in the deep sea, it isn't an abstraction like the future of humanity that makes it all worthwhile. It's the revealing moment the unexpected discovery that leaps across the Gulf and connects our two worlds.
Several years ago, we came across a squid, Guanatus onyx, holding this enormous mass of hundreds and hundreds of eggs. There was no known case of parental care by squids anywhere. Subsequently, we learned that this period of brooding can last from 6 to 9 months. During that period, she doesn't feed while she guards the babies. Once they all hatch out, then she's done with her job and she can die as all other mother squids do. This is the first example of parental care by squids anywhere. There are so many things like this story going on in the deep ocean that we are as yet unaware of. And if the changes that we're making to the ocean prevent us from ever learning those things, if all that were to disappear before we even have a chance to learn about it, then it would be a tremendous loss for us all.